All right, good morning, everybody. Welcome. Happy Tuesday. So hopefully test 2 went well for everybody yesterday, and quiz 4 as well. Um, any before we jump in, any concerns? Anything anybody wants to ask about, talk about? How are we doing? How are we feeling? All right, that kind of morning. Either that or my chat's not working again, but I can at least see everyone in chat this time. Okay, chat test is working good. So the way the testing works is it depends on when CrowdMark receives your submission. That is logged by when you click the submit button, not when everything goes all the way through. Quiz, not test. Okay. So the way the quiz works is after 15 minutes, your answers get locked in. Anything you have submitted stays submitted. So even if it takes you a couple extra seconds to click submit, the system won't have let you change your answers. And it'll just take whatever answers you had at the 15-minute mark. So if you are like 5 seconds late on a quiz, it won't matter. Yeah, it warns you that you submitted late by some 5 seconds, but I think as long as you're under 30 seconds, it doesn't matter at all. And then after that, there's some detail to it that I don't want to say without double checking. But yeah, if you are late submitting your quiz by 5 seconds and you haven't changed any of your answers in that 5 seconds, it was just clicking through the submit quiz, yes, I really want to submit my quiz, then you're fine. Totally good. And just for completeness, on your test, it's whenever CrowdMark accepts your test, and I believe 5 seconds gets rounded down, but it's not a 30-second thing. It's some cutoff. I want to say it's 12 seconds gets rounded down and 13 seconds gets rounded up, but there is some leniency built into the CrowdMark system. It's not configurable. It's just whatever CrowdMark decided. So I wouldn't test it if I were you, but if you happen to run a second over on your test, that's also going to be okay. But try and not push it. Okay, so we have these warm-up questions. Let's get started there. So warm-up A, not a trick question. Should be nice and easy. If we have 5 people, in this case, let's assume these 5 people have different names. They are 5 individual humans. And so the order in which they line up matters. Being first is different than being last. No Ricky Bobbying here. And yeah, so Earl either has the correct answer or is very enthusiastic about the wrong answer. But I'll give him the benefit of the doubt and assume that bifactorial, the right answer there. Right, so we can pick a first person and then pick a second person and then pick a third person and then a fourth and then a fifth. And our first option, we've got 5 choices. And then in our next option, we can't pick the first person because they're already in line. So we've got 4 choices and then 3 choices and then 2 choices. And then once we've placed everyone else, there's only 1 choice for the person at the back of the line. And so this gives us 5 factorial, which happens to be 120. And so now, part B, the question is what happens if instead of in a line, we're arranging people around a circular table? And the question would be, I think, a little bit more precise if this wasn't just a warm-up question. But the idea here is that if I put person A here, B, C, D, and E, that's going to be the same arrangement as putting A, B, C, D, and E. right? It's a circular table, so there is no right way to view it. All we're really worried about is who's on whose left and who's on whose right. So in both of these situations, A, who's sitting down facing towards the table, has B to their left and E to their right. And you can check that that's true for everyone around the table, that these two match up. So we've got some proposed answers from chat, 4 factorial or 24, which are the same number. So how do you come up with an answer like that? What makes it drop from 4 factorial to, from 5 factorial to 4 factorial when we're moving from a straight line to going around a table? Yeah, okay, so one way of thinking about this, good. We've got 2 different ways of thinking about it. I like both of those. So one way of thinking about this is each arrangement, each way of lining up my 5 people corresponds to 5 different seatings around the table. Right, if I fix my seats in place, let's say it's those chairs that are like bolted to the ground, you can't move them around. If I have 5 of those chairs, then I can put A in any one of those 5 chairs and have the rest of the line circle around the table. And so each lineup corresponds to 5 seatings at the table, 5 factorial over 5. Another option is to say, because it doesn't matter, because I can always rotate around, I might as well put A in this position. And then if A actually sat anywhere else around the table, well, I'll just rotate the table until that's where A sits. And now the question is, how many options are there for the person sitting to A's left? Well, there's 4 options. How many to their left? 3, to their left 2, to their left 1, so I get 4 times 3 times 2 times 1 is 4 factorial, which is also the same thing as 5 factorial over 5. So good. We've got 2 different ways of thinking about it. Both give us the same answer. Gives us a lot of confidence that our answer is good. It's a lot harder to get the same wrong answer in 2 different ways. Okay. Good warm-up. Okay, so last time we talked about permutations, and we said that there were n factorial permutations of a set with n elements. And we said if you didn't want to order everything, if you just cared about ordering r elements out of n, there were n factorial over n minus r factorial ways to choose r elements from n elements when order matters. Okay, so this was our situation where you have 10 athletes and you want to fill out a podium. We don't do 10 factorial, because if you're not first, second, or third, it doesn't matter. But we can do 10 times 9 times 8. Pick a first place, pick a second place, pick a third place. Nobody else counts. So next question, though, is what about when order doesn't matter? And so I want to go back to our pizza toppings. So if you remember, Pizza has 37 different toppings available. And when we were trying to count how many different pizzas you could make, we had these 2 competing ideas of how to go about it. One was the one we ended up going with was create a 37-step process where in step 1 you ask, do we have Asiago cheese? Step 2, do we have arugula? Step 3, do we have anchovies? And we just go topping by topping, and each topping there's 2 options: yes include or no don't include. That got us our 2 to the 37 pizzas, just about 125 billion. The other way we thought about trying it, that didn't quite lead anywhere, was, okay, how many ways are there of making a 0 topping pizza? Just 1. How many ways are there of making a 1 topping pizza? 37. And then we asked, how many 2 topping pizzas exist? And at the time, our guess was, because we had been talking about permutations, it should be 37 times 36. Pick a first topping, and then pick a second topping. And the reason that this doesn't quite work out is that we're counting the same pizza twice. Right? This process is using the rule of product. The rule of product is always associated with this method for generating a pizza. So in this case, our method would look like step 1, choose first topping. Step 2, choose second topping. Excuse me. And the issue is that I can create the same pizza twice going through this process in a different order. So maybe I want a sausage and onion pizza. So one way of doing that is first topping, I choose red onion. Second topping, I choose Italian sausage. Also, happens to be one of my favorite pizzas. Just a little fun flavor there. Another way of choosing this same pizza is first topping Italian sausage, second topping red onion. I've gone through the same process, first topping, second topping, in a different order, and so they're counted separately. This was the 37 option, this was the 36 option, this was the 37 option, this was the 36 option, but I ended up with the same pizza. And it's even more egregious if I talk about a 3-topping pizza. So here, what would my process be? I would choose a first topping, and then a second, and then a third. And now I can create the same pizza lots of different ways. So I could do red onion, sausage, green pepper, or I could do green pepper, sausage, red onion, or I could do green pepper, red onion, Italian sausage. These are all giving me the same pizza. I'm counting the same pizza again and again and again. And the problem is that when we do permutation, the order matters. There's a difference between first, second, and third place. But when we're choosing a pizza, the order of the toppings doesn't matter. There is no first topping, second topping, third topping. There's just 3 toppings. And so we need to come up with another way of counting that. And we get at it here. How many ways are there of putting my 3 toppings into an order? Once I've picked my 3 toppings, how many ways can I order them? Yeah, right, I got 3 factorial ways, 6 total ways. So for my 3 topping pizza, how many times does this process generate each pizza? Well, it generates each pizza 3 factorial times. 1 for every possible ordering of the ingredients, of the toppings. So in my 2 topping pizza case, each pizza topping gets counted twice, because I've got 2 toppings and I can put them in one of 2 orders. So how many ways are there to actually generate my 2 topping pizza? Not 37 times 36, because that counts each pizza topping twice. What I actually want is 37 times 36 divided by 2. How many ways are there of generating each 3 topping pizza? Well, 37 times 36 times 35 is how many ways I can pick 3 toppings. But I'm counting each pizza 3 factorial times then. So now, in general, if I have n toppings and I want to pick R, to go on my pizza, how many ways are there of doing that? Order does not matter. Yeah, really good. What I want to do is first, I want to pick my R toppings like R does matter. Pick a permutation of R elements. Which we know we can do in n factorial divided by n minus R factorial ways. Then I want to divide by the number of arrangements of my toppings. Because each different way of arranging my toppings gives me the same pizza counted multiple times. I'm over counting the number of pizzas by a factor of R factorial. So this gives me the total number being n factorial divided by n minus R factorial, all divided by R factorial. But that's a complex fraction. I can simplify it down to n factorial over R factorial n minus R factorial. And this quantity is so important that it gets its own symbol written like this, which we pronounce n choose r. So this is not a fraction. There's no fraction bar here. It's just an n on top of an r inside of parentheses. This means n choose r, and we have a formula for n choose r. The formula is n factorial over r factorial times n minus r factorial. Can I recenter the paper? Sure. Get you that top line. One quick note, just because some of you may have seen this before. This is the notation we're using in this class, n choose r. We do not use n choose r or choose nr. These are not used. The only notation we're using in this course is n choose r written like this. Okay. So, how many 3-topping pizzas do we have? We have 37 choose 3, which, using my formula, comes out to be 37 factorial divided by 3 factorial times 37 minus 3 is 34 factorial. Now, you can ask a fair question. Why do we not let you use calculators in this class? Right? In the real world, you will always have a calculator in your pocket. Growing up, I was told I wouldn't. That was just wrong. Now I have a cell phone, not only has a calculator, it has access to the world's most powerful computers over the internet, which can do this for me. Well, it's worth knowing that most calculators that are just calculators can't actually do 37 factorial. If you plug 37 factorial into anything but a real computer system that's built to do mathematics, it can't handle it. 37 factorial is real big. It's bigger than 10 multiplied by itself 27 times. So 10 to the 27 power is real big, and it's 37 factorial is even bigger than that. But I can still calculate this by hand, because I can think through how this calculation works. Right? What does this look like? This is 37 times 36 times 35 times 34 times 33, all the way down to times 2 times 1. And I'm dividing that by 3 factorial, which is 3 times 2 times 1, times 34 factorial. Well, what's 34 factorial? 34 times 33 times 32, all the way down to times 2 times 1. So because everything here is being multiplied or divided, I get a lot of cancellation. Everything in here cancels. And what I'm really left with is just 37 times 36 times 35 divided by 3 times 2 times 1. And this calculation is much more reasonable to do by hand. I can see that my 3 times 2 is 6. I can cancel that 6 with my 36. And I get 37 times 35 times 6. which I've worked out ahead of time, comes out to the very pleasing number 7,770 three-topping pizzas. So it's important to know how these things work and not just plug them into a calculator and have a calculator multiply together these gigantic numbers when really most of that is getting canceled out. So being able to do these calculations without a calculator is not so much about can you replace a computer, because of course not, but do you have a good enough understanding of what's going on that when the calculation is actually simple, you can just do it in your head and move on. So, by the way, I went through and tried to come up with what I think might be the least appealing of these 7,770 pizzas. I'm certainly biased by my own tastes, but my vote for worst pizza here would be anchovy plus jalapeno plus goat cheese. I think if you are having a party and this is the three-topping pizza that you order, it's going to be a little hard to get rid of. But feel free to come up with your own worst three-topping pizza. What is that? That is how you get the whole pizza to yourself when you order a pizza at a party. Don't know if it's worth it, but it would probably work. Okay, let's do some examples with combinations with n choose r. So example 1. So remember our lottery. The way we had talked about our lottery originally was that you chose 6 numbers, all 1 through 6 numbers, all 1 through 69. And we assumed that there was replacement, so you could get the same number again. But when they actually choose the lottery numbers, at least for the Powerball, there's no replacement. They just have these numbers 1 through 69 in a giant tumbler, and they pull them out one by one, but the numbers don't go back in between. So if I get rid of this with replacement, and I say without replacement, now how many different lottery numbers are there? How many different lottery cards? So I'm picking 6 numbers between 1 and 69, but I'm not replacing them in between. The other way of thinking about that is if you buy a ticket, what are your odds of matching exactly the numbers in exactly the order? We've got a numerical value, which may or may not be right. I'm not sure. What is that in terms of factorials and such? 69 choose 6. Good. This is what I was looking for, because it's not the right answer. So remember, the order of the numbers you pick still matters. There's still a difference between 1, 2, 3, 4, 5, 6 and 6, 5, 4, 3, 2, 1. So here, order matters on your lottery card. So I want my 69 times 68 times 67 all the way down, or 69 factorial divided by 63 factorial. I'm choosing a permutation of 6 numbers. Now we'll get to the question that you wanted me to ask. Here's part A. Part B is, if this is how you win the jackpot, now we'll make the minor prize just match the 6 numbers. I don't care about the order. You just have to have the correct 6 numbers. How many cards match all 6 numbers? Order doesn't matter. Now I'm just choosing 6 numbers from 69. Now I have 69 choose 6. And by the way, for this course, these are perfectly good ways of answering this question. I do not expect you to evaluate this, let alone this. I don't expect you to be able to do 69 times 68 times 67 times 66 times 65 times 64 without a calculator. It's not worth anybody's time. And then to divide by 720 when you're done with all of that, not interested. Not super important. There is a part C to this question, though. Let's say you're superstitious. You want to pick 6 numbers, but you want at least one odd number. How many ways are there to win a minor prize if you always buy tickets with at least one odd number? So now we're choosing 6 numbers from 69, but one of them has to be odd. Or 2 or 3, or 4 or 5 or 6. Any of those are fine. So here's one option. 1, 2, 3, 4, 5, 6. That's fine. I can have 2, 4, 6, 8, 10, 11. That's fine. I'm never ever going to buy 4, 8, 16, 32, 64, 12. Doesn't have any odd numbers. So that one's no good. Okay, so we've got some good ideas here. We can fix one place. And then we've got 69 choose 5. And right, remember, we're not asking for order matters here because we're not asking for the card that you buy. We're saying you want to just win a minor prize. So you just want to match. You want to match all 6 numbers, but you want one of them to be odd. So another way of asking this question is, how many ways can you choose 6 numbers where at least one of them is odd? So fixing the place gets a little bit rough, because we've got 6 ways to choose the place, but order doesn't matter. There's a better way of thinking about this problem. It turns out we don't actually have to choose which number to fix. The best way of thinking about this problem is that there are 69 choose 6 ways to pick any 6 numbers. how many ways are there that don't work? Oops, you can't see what I'm writing. How many selections of 6 numbers don't satisfy my rule that there's at least one odd number? Well, if there's not one odd number, that means they're all even numbers. How many even numbers are there between 1 and 69? Good. Got 34. 2, 4, 6, 8, 10, 12, all the way up to 68. So half of the numbers from 1 to 68. 34 numbers. If I wanted all of my numbers to be even, I have to choose all 6 of my numbers from those 34. 34 choose 6 is the number of ways that don't work. So how many ways are there that do work? There's 69 choose 6 total ways. Subtract off the cases that don't work. Yeah, really good. So 69 choose 6 minus 34 choose 6 is the number of ways I can choose 6 numbers such that at least one of them is odd. Because I've just subtracted off all the ones where they're all even. Nice. Okay, let's do one more example and then we'll take our quick break. Now I want to ask, how many ways, if we have 20 players, how many ways can teams A, B, C, D, and E draft the players so that each team gets 4 players? And let's say that the order, the draft order is fixed. So A is going to pick first, and then B, C, D, E, and then it'll go back around to A again. So we've got a good thought in chat. This was one of those where I was hoping somebody was going to give me the wrong answer first. So what's the wrong answer? What's the thing I'm hoping someone's going to say, but it's not that easy? You're all still too smart. I was hoping somebody was going to say, we got 20 players. We're drafting them. There's a first pick, a second pick, a third pick, a fourth pick, a fifth pick, and so on. So 20 factorial, right? Just line them all up. First pick, second pick, third pick. 20 choices for first pick, 19 choices for second pick, 18 choices for third pick. But it's not so simple. Because... oh, good. All right. I tricked somebody. They just weren't bold enough to put it in chat. So let's start with this. Y is 20 factorial. wrong. And the reason 20 factorial is wrong is that if I put, let's say Albert gets first picked by team A, and then Beth gets picked, and then Charlie, and then Daniel, and then Alice. These are my first 5. The teams end up looking the same if I swap Albert and Alice. If Alice is actually a first pick and Albert's a 5th pick, or if Albert's a first pick and Alice is a 5th pick, the teams end up looking the same. It doesn't matter which one got on the team first. At the end, team A has these 2 players on it. And it doesn't matter which one we picked first. So, okay, let's go through some of the other answers from chat. So, 20 choose 4 times 5. So 20 choose 4 makes a lot of sense that this is going to show up in our answer somewhere. 20 choose 4 is the number of ways to form team A. If I'm just saying I want to build a team, there's 20 players, I need 4 of them. There are 20 choose 4 ways to pick team A. And now we got to think about team B. So what comes next? So some options suggested from chat. We could have plus 16 choose 4, or maybe we could have plus 20 choose 4 again, right? This would lead to 20 choose 4 times 5 if I added 5 of these together. This one adds to 20 choose 4 plus 16 choose 4 plus all the way down to plus 4 choose 4. So what's the right thing to do? Well, first of all, where are these pluses coming from? If we see a plus, plus means that we're doing rule of sum. Good, rule of sum. So is this a rule of sum situation? Are we picking members for team A or members for team B? Or is this a rule of product situation? Are we doing a process where first we pick members for team A, and then we pick members for team B? Yeah. So this is gonna be a rule of product situation. This is more of a process. First, we're gonna pick our members for team A, and we have 20 choose 4 ways of doing that. Next, let's pick our members for team B. This is the next step in the process, so we're multiplying. And how many ways are there to choose the players for team B? Each player can only play for one team. Good. We got 16 choose 4. There are 16 players left over. Once we've selected our 4 players for team A, our second step is to choose players for team B. Now, which players are left changes anytime you go through this process. Depending on who's on team A, there's a different number of ways to make team B, but the number of ways to make team B is the same. Remember, that's all we need for rule of product. The number of ways is that there's 16 players left over, we choose 4 of them. So now we make team C. We've taken 4 players for team A, another 4 players for team B. We've got 12 players left over for team C. For team D, we've picked 12 so far. There's 8 players left over. And then for team E, we're down to our last 4 players. this is what we've got. And this actually turns out to be, I mean, it's a big number, but there's a lot of simplification that goes on here. You look at this, what we've got is 20 times 19 times 18 times 17. Excuse me. And then there's a 16 factorial, which cancels with the 16 factorial in the denominator. And then here, 16 times 15 times 14 times 13. And then there's a 12 factorial, which cancels with the 12 factorial down here. And then 12 times, so we actually end up with 20 factorial in the numerator. And we end up with 4 factorial, 4 factorial, 4 factorial, 4 factorial, 4 factorial in the denominator. So this is the same as 20 factorial over 4 factorial, 4 factorial, 4 factorial, 4 factorial, 4 factorial. And this actually also has a special name. So this is the multinomial coefficient, which we'll talk more about on Thursday, which we write 20, choose 4, 4, 4, 4, 4. This is, by definition, 20 factorial over 4 factorial, 4 factorial, 4 factorial, 4 factorial, 4 factorial. And in fact, if we have any number n that's equal to k1 plus k2 plus all the way up to some kj, the multinomial coefficient n choose k1, k2, k3, all the way up to kj is equal to this n factorial over k1 factorial times k2 factorial times kj factorial. Okay, that's a good place to pause, take a quick break. So go get a snack, get a drink, stand up and stretch, whatever you need. Come back in 2 minutes at, let's say, 9:21. It's just about 9:19. So take 2 minutes. We'll come back. We'll talk more. Okay, I got 9:21, so let's gather back together wander back over to your desk, settle back in, refocus for our final 25-ish minute push. Okay, so now that we're familiar with combinations, which is what we give the name to this n choose r kind of thing, let's prove something about them. Right, this is a proof-based course. So here's a theorem. For all n and r in positive integers with n greater than or equal to r, n choose r is equal to n choose n minus r. Okay. So let's prove this. And I'm going to prove this theorem twice. The first time I prove this theorem, I'm going to do it the way that you might think about first. So n choose r is by definition n factorial divided by r factorial times n minus r factorial. Right, this is by the definition of this is called the binomial coefficient. Right, this is the multinomial coefficient. When we just have this, it's the binomial coefficient. N choose r. And thinking ahead, my last step, I want my last step to be equal to n choose n minus r. And n choose n minus r is n factorial over n minus r factorial times n minus r factorial. This is, again, this last step is going to be by the definition of the binomial coefficient. So really, I just want to show that these two things are equal. And it turns out that n minus r is exactly r factorial. So really, the only step I need is to swap the order of everything in my denominator. This is because multiplication is commutative. And now r factorial is equal to, or even better, r is equal to n minus r. Right, the n's cancel and the minus signs cancel, and I end up with positive r. So all of this was maybe squished in to fit on the paper, and I did it out of order. These are maybe my notes, and then I would go back and write up a nice proof. This is equal to this is equal to this, and then I would mention r is equal to n minus r, so that's equal to this, and then my last step is it's equal to n choose n minus r. Okay, so this type of proof is correct. There's nothing wrong with it. It's valid. And it's what we call an algebraic proof. It's an algebraic proof because it's just moving around the symbols to show that these two things are equal. So now I want to go back to my theorem and think about it again, and think about it a little bit more carefully. So what are we really saying when we say that these two things are equal? What I'm saying is, if I have n things and I choose r of them, again, order doesn't matter, that's equal to having n things and choosing n minus r of them. So, in other words, I'm saying if I have n objects, how many ways are there to pick r that are special? That's the same as having n things and picking n minus r that are not special. Anytime I single out r elements and say, you guys are the ones I'm choosing, there's always n minus r that I'm leaving behind. And this gets at the idea of a different type of proof, not an algebraic proof, but a combinatorial proof. In a combinatorial proof, we argue that things are equal because they count the same thing. Quantities are equal if they count the same process in two different ways. So here's an alternate proof of that theorem that we just proved. N choose r is equal to n choose n minus r. We count the number of ways to, and let's make it specific, right? You can come up with a story. This is a proof, but we can be a little bit creative. So let's say we count the number of ways to put r toppings on our pizza. To choose r toppings out of n on our pizza. Method 1 is to choose the r toppings that go on the pizza. And we know the number of ways of doing that is n choose r. And method 2 is to choose the n minus r toppings that we don't want. And everything that's left over is what ends up on our pizza. So you can imagine you're sitting around a party, there's a special. A pizza is cheap if you put r toppings on it. And everybody wants a cheap pizza. But it's really hard to agree on what toppings you do want, right? Some people really like sausage. Some people really like pepperoni. And so what you do is you go around in a circle and you say, okay, everybody gets to eliminate the topping that they want least. And when there's only r toppings left, those are the r least objectionable toppings. That's what we'll order on our pizza. Right? So you're not going to end up with anchovy jalapeno goat cheese, because as soon as it gets to my turn, I'm eliminating anchovies. If that's still left, it's not going on our pizza. Sorry. So method 2, choose the n minus r toppings that aren't on the pizza which there are n choose n minus r ways, everything left, everything left goes on the pizza. Okay. So I've counted the same thing. How many ways are there to make an R topping pizza in two different ways? So that must mean these two quantities are equal. So if we compare these two proofs, algebraic proof, combinatorial proof, both prove the same theorem. The combinatorial proof has a nice little story that goes along with it. In some sense, it's explaining why these two quantities are equal. It's not just that the math works out, but something about what they're counting is counting the same thing fundamentally. So a lot of the times we like combinatorial proofs. Now in this case, you might look at this and say, nah, I still like the algebraic proof. I think it's a little bit easier. And that's fine. So I want to do another example where I think the combinatorial proof actually is even nicer than the algebraic proof. So we have seen the following theorem. The sum I starts at 1 and goes up to n of I is equal to n times n plus 1 divided by 2. But now I can finally write this in the way it should be written, which is n choose 2. Sorry, n plus 1 choose 2. Let me actually just rewrite that. Right, n plus 1 choose 2 is n plus 1 factorial over 2 factorial. Let's just do this out. N plus 1 factorial over 2 factorial times n plus 1 minus 2 factorial. This is n plus 1 times n, and then I've got an n minus 1, n minus 2, n minus 3, all the way down to 1. That's exactly what I have here. Plus 1 minus 2 is n minus 1, n minus 2, n minus 3, all the way down to 1. And then 2 factorial is just 2. So, okay, I have this sum is equal to n plus 1 times n over 2. We've seen how to do this with an algebraic proof. Right? Use induction. So we've got to do a base case. We have to prove it for I equals 1. And then our induction hypothesis. We do our induction step. We sum up to n plus 1. We pull off one of the terms. We use our induction hypothesis. We combine everything back together algebraically. It ends up looking like the right thing. So the answer is true by induction. I want to go back and prove this theorem again using a combinatorial proof. So here's our combinatorial proof. I need to find something to count on both sides. And on the right side, it's telling me what to count. N plus 1 choose 2 means I have n plus 1 things and I want to choose 2 of them. So let's make it a little bit more specific again. Suppose I want to choose 2 numbers out of 1, 2, 3, all the way up to n plus 1. So method 1 is I choose the two numbers. Right? How many ways are there to pick two numbers out of n plus 1? There's n plus 1, choose two ways. Okay. So far everything is nice. Now I need to come up with a method 2. I need to come up with another way of picking two numbers that's going to be counted by this sum. So here's my question. What have we seen in counting that makes a sum come up? When do we add numbers in counting? What rule has to do with adding? Yeah, really good. If you see adding, you should think rule of sum. You need to think about cases. So somehow there's n different cases that I'm thinking about here. I've got to break this up into n different cases. So I'm trying to pick two numbers, and I want to break it up into n different cases. And the thing that works, and I know it works because I thought about it ahead of time, but this is a leap. This takes some thinking, some pondering, some trying stuff to come up with, is I'm going to break into cases based on what my biggest number is. Break into cases based on the biggest number, or bigger number, I should say. There's only two. We're only picking two numbers. So bigger number. Okay, so case 1, my bigger number is 1. How many ways are there to pick two numbers without replacement if the bigger one is 1? This is a trick. Yeah, there's no way of doing it. 0 ways. So I don't even have to consider this case. You can't have two numbers where 1 is the biggest one if 1 is also the smallest number in your list. So case 1, we don't actually even have to consider. Case 2, if your bigger number is 2, how many ways are there to pick two numbers if the bigger one is 2? There's only one way of doing it. Your other number had better be 1. So there's one way here. And that's picking the set 2, 1. Doesn't matter what order. Just 2 and 1 are in my set. Okay, case 3. The bigger number is 3. Now how many ways can I do it? I've got 2 different ways. Right? I can pick 1 and 3, or I can pick 2 and 3 ways. If 3 is the bigger number, I've got 2 ways of doing it. And now let me skip ahead a bit. What about case K? Or even better, I'll call it case I, where the bigger number is, well, based on how I'm labeling this, yeah, that's fine. The bigger number is I. How many ways are there? I minus 1 ways. Good. And what's my last case? what's the biggest number I have to worry about? Sorry, I'm really squeezing this in at the end. What's the biggest number that can be my bigger number? Not I plus 1. Also not n plus 1. Right? I'm choosing two numbers out of 1 all the way up to n plus 1. So n plus 1 is my last case. So now your bigger number is n plus 1, which leaves me with n ways. So now I look at my list of all the different ways I have. Rule of sum says I can add them all up because they're all disjoint. If the bigger number is I, then it's not I minus 1. If the bigger number is n plus 1, it's not 3, any of those. So all of these cases are distinct, which means I can add them all up, which means I'm adding 0 plus 1 plus 2 plus 3 plus I minus 1 all the way up to plus n. So I'm adding up the sum from I equals 1 to n plus 1 of I minus 1. But that's the same thing as saying I'm adding up from I equals 1 to n of I, because I'm just getting rid of this 0 case. And so this left-hand side counts the same thing. Both quantities are counting the number of ways to choose two numbers between 1 and n plus 1. So this is a combinatorial proof that these two things are equal. And I think the combinatorial proof is nicer than the algebraic proof. And there's two reasons for that. One, the algebraic proof, it just kind of comes out of nowhere, right? The induction works, but only because you know the answer. You're using the answer to prove the answer is right. And there's nothing logically wrong about that, but it's not satisfying because you can't really come up with the answer on your own. You just prove that it's the right answer. But the nice thing about the combinatorial proof is now that you've seen this idea, you can actually come up with equalities that before you would need the answer to, if you were going to prove by induction, you'd need to know the answer ahead of time. But now if I show you a sum, like the sum from I equals 1 to n of n choose 2, of I choose 2. So this is the sum I equals 1 to n of I times I plus 1 over 2. We can figure out what this answer is by thinking about the combinatorial proof. What does this count? If n is the biggest number, or if n plus 1 is the biggest number, n plus 1 is the biggest number, there are n choose 2 ways to pick two smaller numbers. And if I, excuse me, if I plus 1 is the biggest number, there are I choose 2, which is equal to I times I plus 1 over 2, ways to choose two smaller numbers. So what am I counting here? What is this sum equal to? If I was going to do a combinatorial proof, and one way of doing this process is this: pick the biggest number, then pick two smaller numbers. What is this process counting? the last example was choosing two numbers between 1 and n plus 1. What is this process counting? All right, we are over time, so I won't pause too long. Here we're counting three numbers. Between 1 and n plus 1. I pick my biggest number, and then I pick two smaller ones. So this sum is going to be equal to n plus 1, choose 3. Because I'm just counting this process in two different ways. Okay, sorry for running a couple minutes over. I will stop there. See everybody on Thursday for a lecture.